Hello! For today's topic, we have electrochemistry. This is the area of chemistry where electricity and chemical reaction are involved. So electrochemistry deals with the interconversion of electrical energy and chemical energy. The electrochemical process are redox reaction in which the spontaneous reactions release energy which is converted to electricity, which takes place in a Voltaic cell, or the electricity is used to drive non-spontaneous chemical reaction. This process is called electrolysis, and this takes place in an electrolytic cell. In both type of electrochemistry or branch area of concern for electrochemistry, an electrodes is important. And these are electrically conducting sites at which either oxidation or reduction takes place. There are two types of electrode. We have the anode electrode, where oxidation reaction takes place, and the cathode electrode, where the reaction takes place. In both cases, whether Voltaic cell, where electricity is produced by a chemical reaction, by a spontaneous chemical reaction, or electrolytic cell, where the chemical reaction is produced by electricity, a non-spontaneous chemical reaction that is driven by electricity. In electrolytic cell, design of the electrode differ from each other. However, oxidation always takes place at the anode and reduction takes place at the cathode. Okay, for voltaic cell, the anode is negatively charged, whereas for electric cell, it is positively charged. And the cathode for voltaic cell is positively charged. On the other hand, for electrolytic cell, it is negatively charged. And you have to remember from our previous discussion on redox reaction that the species undergoing oxidation is referred to as reducing agent. And the species undergoing reaction is referred to as oxidizing agent. Because during the oxidation reaction, a species has to lose electron. And when he loses electron, there must be a species accepting this electron. In effect, its state is reduced or it undergo reduction reaction. So the species that give off electron undergoing oxidation reaction is referred as the reducing agent. On the other hand, the species that accept the electron given by the species that loses the electron undergoes reduction reaction. Therefore, it is the one that oxidizes the species that is losing electron. To begin with, the first branch of electrochemistry, where in spontaneous reaction release energy, which is converted to electricity, called Voltaic cell, we can represent the Voltaic cell by a schematic diagram here, where we have two compartments here. We have the anode compartment and the cathode compartment. And in the anode compartment, we have an electrode. Let's say it's zinc electrode. At the cathode, we have a copper electrode. Okay, at the anode compartment, it is the zinc metal will give off two electrons to undergo oxidation reaction. So what happened is the zinc electrode here is giving off electron and producing positive ion, the zinc positive ion. Okay, since in this compartment the electron is migrating towards the other electrode, therefore since electron is coming from this direction, hence this electrode is negatively charged. The anode in a voltaic cell is negatively charged. On the other hand, at the cathode compartment, since the electron is migrating from this direction to this direction, unlike sign attract each other, therefore the cathode is positively charged and the reaction is the copper ion from the cathode aqueous solution plus the two electrons coming from that direction from the anode produce copper metal solid. So this will accept the two electron coming from this electrode, and it is positively charged because unlike sign attract each other. Okay, so as this electrode releases electron, and in effect cation, positive zinc ion. Okay, the cation from the aqueous solution in the cathode compartment will accept. As this cation increases in the anode, the cation decreases in this compartment because it is the one that accepts the electron coming from the anode to the cathode. When there is not enough electron coming and the anode here is used up, then there would be no cell voltage that can be recorded. The cell voltage can be recorded or can be measured by attaching an external circuit to the two compartment or two half cell. Okay. To complete the circuit, a salt bridge is provided, and this allows the ions to flow into each half cell. The bridge closes the circuit and allows current to flow. Without the salt bridge, the local charges will build up on both electrodes. Okay? Thus, neither electrode reaction will proceed, so no cell voltage can be measured. So, as the flow of electron is from anode to cathode, the flow of ions in the salt bridge is the negative ion or the anion in the salt bridge. This is your salt bridge. The salt bridge is filled with a solution of a strong electrolyte, meaning they are 100% ionized in water. So, as the positive ion is produced when electron is given off in this terminal, the negative ion, the anion of the electrolyte in the salt bridge must be coming or flowing in this direction. On the other hand, the positive or the cation in this compartment is being used up by the acceptance of two electrons undergoing reduction from positive 2 to 0 in the case of copper. So to supplement that decrease in the positive ion or cation, the cation of the electrolyte in the salt bridge must be flowing in this direction. Then, the electron is flowing from anode to cathode in a Voltaic cell, and the ions from the negatively ion or the anion is flowing, the movement is towards the anode, and the cation from the electrolyte of the salt bridge is moving towards the cathode terminal. Or we can represent the Voltaic cell in two ways. One is using an overall cell reaction. The electrochemical cell is represented by the overall cell reaction by adding the two half cell reaction. Okay, the anode half cell reaction and the cathode half cell reaction. Okay, here we have the zinc. If you add the two, we have the copper ion. The two electrons will cancel out because they are present in both sides of the equation. And your product, the zinc ion and the copper as the electrode. So as this size diminish, there is accumulation of or deposit of the copper metal around this electrode or the cathode. Or another way of representing your Voltaic cell is by using an electrode reaction. So this is how we read it. The zinc electrode, okay, the single slash is the phase boundary, solid. Then we have the aqueous, zinc ion, the cation of zinc. We have the double slash, which represent the salt bridge. Then we have the copper ion in the aqueous solution. Then the phase boundary and the electrode, solid electrode of copper. Again, the single slash represent the phase boundary, solid, then aqueous. Then the double slash, the salt bridge. Then we have the cation, single slash, phase boundary, and the electrode, the solid electrode. Now, how do we determine the potential of the two-half cell? And that is called the electrode potential. The electrode potential is the voltage or the electromotive force of a cell, which is measured in volts. It is the sum of two half cell potential using the standard potential value. The standard potential value were established by comparing the potential of the cell with the reference cell. It is the hydrogen electrode whose potential is 0. Most standard electrode potential tables gives only one value, and it is usually the reduction potential. Okay. The hydrogen is used as the reference cell, which has a potential of 0. That is the standard condition. For aqueous solution, the concentration is 1 molar. For gases, it is 1 atmosphere. Okay, the sign will tell you that the reaction will proceed. If it's positive, the reaction will proceed as it is written. And the negative sign here that is with respect to hydrogen reference cell, okay, as your reference cell. The negative sign here would indicate that the reaction will not proceed as written. Instead, it will proceed the reverse of the arrow or the backward direction with respect to hydrogen as the reference cell. For example, if we want to determine the potential of a half cell cadmium, in this table, the cadmium ion plus 2 electron would give you cadmium solid will have a potential, a reduction potential of negative 0.40 volt. That is undergoing an reduction reaction. Since the table is specifically specified, this is the standard reduction potential in an aqueous solution of 1 molar concentration at 25 degrees Celsius, meaning the aqueous solution is 1 molar cadmium. The salt of cadmium is a strong electrolytes, cadmium, that would make it very soluble in water. Okay. Now, if the cell is taken as oxidation in the anode, because reduction would take place at the cathode, if it's at the anode, referring to the anode half cell reaction, we take the negative of the value that is stipulated in this table. So that means if the cadmium undergoing oxidation, the value would be the negative of negative, it will be positive 0.40 volts. Okay. The E values are also useful for evaluating redox reaction. Substances with high positive reduction, this is above hydrogen with respect to hydrogen being 0, are a strong oxidizing agent, meaning they have a greater tendency to be reduced. And substances with high negative reduction potential or with high positive oxidation potential are a strong reducing agent. They have a greater tendency to be oxidized with respect to hydrogen. So as we can see in this table, substances are arranged from least active metal to the most active metal. Therefore, less active metal has a great tendency to be reduced, and the more active metal here has a greater tendency to be oxidized. If you remember your lesson in the writing of balanced chemical reaction or predicting product of reaction for single replacement, where you have the reference for the activity series of metal. Okay, you have a decreasing, okay, activity here. We have the metals above hydrogen. Again, hydrogen is the reference metal with respect to activity. Okay, we can adopt a mnemonic to memorize this because it is very important that you know the activity series of a metal in case you're working in the future in the field. You don't need to grasp a chemistry book to determine whether a metal is a specific metal rather is more active than the rest, or it will whether it will react with hydrogen in the acid or not. Okay, we have here the mnemonic: Lily for lithium, Peter for potassium, Vari for barium, Clark calcium, sodium for maid, magnesium, aluminum, monkey manganese, zebra zinc, carry chromium iron itself. We have cadmium, you can represent it by C. Then we have nail for nickel, to tin, liver for lead. And we have a period here, meaning the activity stopped. Then we start with He. It's not helium, it's hydrogen. Okay, the hydrogen is a reference. Then we have He, caught, copper, Ben, bismuth, antimony, Mexican for mercury, rather, silver for silver, plated for platinum, and gold for gold. So it rhymes this way. Lily, Peter, Barry, saw, Carl, made a monkey, zebra, carry, iron, sea nails, two liver full. He caught Ben, a Mexican silver plated gold. Okay, you may start memorizing it by heart. So when you have the chance to work in the field and you have meet a situation where you have to decide which is more reactive than the other, then you would have a reference by heart without grabbing a chemistry book. Okay, we'll go back to this mnemonic later in determining which will be the anode and which be our cathode. Okay, the active metal should be the anode and the less active metal should be at the cathode. Okay, likewise in this table we can have a reference here. The positively charged bolt here has a greater tendency to be an oxidizing agent, meaning they have to undergo reduction. And this species which has a negative sign has a greater tendency to become a reducing agent. So these are probably the one that is below is the anode. These are active than the one that is above the hydrogen in this table. They have the same principle anyway. Okay, for the electrode potential, moving on, the cell potential or the EMF is very important because it is related to the maximum electrical work that can be obtained from an electrochemical cell. And the standard potential of a cell, it is the condition, this table that we have preparing a while ago. This would be at the condition that all the ions concentration are 1 molar. The temperature is at 25 degrees Celsius and the pressure is 1 atmosphere for gases. If the condition other than this is not met, then we have a non-standard condition, which will be our next topic later. Okay, so the standard potential value are an intensive property. Hence, they are not affected by the change of stoichiometric coefficient during balancing. Unlike in the thermochemistry, in the thermochemical equation, since the heat involved is a molar heat, when you multiply the chemical reaction, the thermochemical reaction by a coefficient, the heat associated to that reaction is likewise multiplied. However, for standard potential value, they are not affected by the change in the stoichiometric coefficient during the balancing of the equation. We balance that only to determine the total number of electrons being transferred. Okay, we change the stoichiometric coefficient necessarily if the number of electrons that is lost is not equal to the number of electrons that to be gained by the other species. So we have here an example where the cadmium the undergoing oxidation is multiplied by 2 for every cadmium For 1 mole, you have 2 electrons giving off to undergo oxidation from 0 to positive 2. But the potential is not multiplied by 2. Remember, a while ago we have positive 0.40 for the oxidation reaction of cadmium to cation of cadmium. Okay, likewise, the cell potential values determines whether the proposed Huff's reaction will occur or not. As we discussed a while ago, if the value is positive, the reaction is spontaneous and will occur as it is written in the table. If the value is negative, the reaction is non-spontaneous and it will not occur as it is written. However, if the half reaction are reversed, the oxidation becomes reduction, or vice versa, the reduction becomes oxidation, the reaction will occur. If the standard potential of the cell of a non-spontaneous reaction is measured in the laboratory with a voltmeter, and the reading is negative, all you have to do is to reverse the electrode. The cathode becomes the anode, and the anode becomes the cathode. So for the reaction to be spontaneous, the more active metal or reactive metal is placed in the anode and the less active metal is placed in the cathode. Because in a voltaic cell, electron will always flow from a more to less reactive metal. Then how we do know whether the metal is active or not? I give you the mnemonic and that would be our reference later on. The metal above the other is more active than the species below it. Or likewise, if you are referring to the table of electrode potential, if the species is more negative with respect to reduction, then it is in the anode. Okay, if the species is more positive, has a more positive reduction potential, then it's probably in the cathode. Okay. Now, let us have the following example where we can compute the standard electrode potential. So here, for each of the following, we have 6 electrochemical reaction here. We're asked to write the overall cell reaction, all the cell representation. Then you're asked to calculate the standard cell potential, E naught, and determine whether the cell is spontaneous or non-spontaneous. Okay, we have here the zinc and the nickel involved. And for number 2, we have lead and tin. And we have here the aluminum and magnesium. Remember, in the cell notation, the first that is mentioned is the anode followed by the cathode. Okay, the anode is separated by the salt bridge from the cathode. Okay, so we have calcium and chromium, magnesium and iron, then we have chlorine and bromine gas here. Start with, let us have the number 1. We're asked to determine whether the cell that is composed of zinc and plus nickel ion will give you the product zinc ion, and the nickel is an spontaneous given the overall cell reaction. Okay, using your knowledge on redox reaction, assigning oxidation number for each species, we have zinc here 0, nickel positive 2. Okay, we have nickel here 0 at the product. So the one that undergo oxidation reaction must be at the anode. So from 0 to positive 2, it is the zinc undergo an oxidation reaction. We have zinc ion in aqueous plus 2 electron. Referring to our table of standard electrode potential, correspondingly, the potential for zinc is negative 0.76 at reduction. So the negative of negative 0.76 volt, because we have the reaction for that is reduction reaction, and this is oxidation reaction. So we take the negatives of the negative or the reverse of the sign. For the cathode, we have the nickel plus 2 electron undergoing reduction from positive 2 to 0. And with your from your table, nickel undergoing reduction is negative 0.25 volts. Okay, we take the sign as is because it is a reduction reaction. Okay. So for the potential, this is positive. That would give you 1. So that is positive 0.51 volts. And since there are 2 electrons on both sides, so that will cancel out. So you have zinc plus the nickel will give you the zinc ion and the nickel metal. Okay, as given. So we can write now the cell notation or the electrode reaction. Okay, we have here the zinc solid single slash, which is the phase boundary. You have the zinc ion in aqueous, the double slash, the salt bridge. Then you have the nickel and single slash, you have the nickel solid. Okay. For the next number, we have lead and tin. Okay, so lead is 0 here. You have the stannous ion. You have the plumbous ion in the product and tin in the solid state. Okay, elemental state 0. So from that, we have 0 to positive 2. It is the lead that undergo oxidation reaction. So we have here we lose 2 electrons to undergo oxidation to positive 2 plumbous. Okay, again, from your table, standard potential, you have lead here. That is negative. So the negative of negative 0.13 volts. Okay, because this is reduction reaction, so we take the reverse of the sign. Then next we have stannous plus 2 electron give you the tin solid state. Okay, using your, again, referring to your reduction potential table, we have 14, that is negative 0.14 volts. So if you take the sum, that is positive, that is negative 0.01 volt. Okay, so the sum of the two half cell reaction would be the overall cell reaction, which is the given as well. So we can write the cell notation for this. You have the lead ion, the slash, you have the tin ion, single slash tin. However, the sign negative here means the cell is non-spontaneous. To make it spontaneous, you revert the anode and the cathode. You will make the cathode be the lead and the anode be the tin. Okay. In the first example, we have a positive. The cell is spontaneous. So the reaction will take place as is it. But in this case, there will be no potential that will be recorded. It is negative. So there will be no current or electricity that will be flowing if you take them as is. It the anode should be the tin and the cathode should be the lead. Okay. Referring to our activity series, that tin is more active than lead, so tin should be at the anode and lead is in the cathode. Moving on, for the third example, we have here the aluminum and magnesium. Again, aluminum here is 0 and magnesium here is 0. So aluminum, we're given here the cell notation. By the way, if you're given here a cell notation, the first represent the anode, and after the salt bridge, that represent the cathode. Okay, so from that we can have a reduction, an oxidation reaction for the aluminum. That is, aluminum solid would lose 3 electrons, okay, to become positive 3. Okay, from your table, aluminum is negative. So negative of negative 1.66 volt. Okay, we take the reverse of the sign because this is reduction potential and this undergoes oxidation reaction. For the cathode, we have magnesium has to accept 2 electrons to be reduced to magnesium. Okay, using your table of reduction, magnesium undergoing reduction is negative 2.37 volts. Okay, so this is positive 1.66 and this is negative, so the sum is you have 1, then 0.71 volt. This sign negative, therefore the cell is non-spontaneous as well. For the overall cell reaction, there must be total transfer of electron. So we have to multiply the first reaction by 2 to make this 6 electron and this by 3 to make the total transfer of electron equal to the gain and loss. So we have the overall cell reaction is 2 aluminum solid plus 3 magnesium ion in the aqueous solution would give 2 aluminum ion positive 3 in the aqueous solution and 3 magnesium solid. The number of electrons will cancel out since they are present on both sides of the equation. The potential here is negative 0.71 volt. Therefore, the cell is non-spontaneous. So what you're going to do, the anode must be the magnesium and the cathode is aluminum. Only the sign will be altered, but the reaction is still the same. Okay. Only the electrodes are interchanged, and when you interchange that, this will become positive. Okay. Okay, referring to the activity series, magnesium is more active than aluminum. So magnesium should be the anode and the cathode is aluminum. Moving on to the fourth number, we have here calcium anode and chromium as your cathode. Okay, this is your anode and this one is your cathode. Okay. For the anode, we have calcium. So you have calcium solid undergoing oxidation. You have calcium ion plus 2 electron. Again, in reference to your table for calcium, we have negative 2.87 volts. Okay. And that is a reduction. So we have it positive. We take the reverse of the sign, the negative of a negative. Okay, that is positive. Okay. Now next we have chromium undergoing reduction. So chromium positive 3 needs 3 electrons to be reduced to chromium 0. Okay. And for chromium undergoing reduction is negative 0.74 volts. Okay, if you take the sum of the two, the potential of the cell would be positive. Okay, you have 3, 1, 2 volts. Okay. So for the overall cell reaction, we multiply the first reaction with the anode reaction with 3 and this one with 2 so that they would have equal number. So this would become 6 electron and this also 6 electron. Okay. So the technique of multiplying them to make the number of electrons equal is the technique that you have done in balancing redox reaction, where you cross multiply the species that gain with the number of electrons that is lost by the other species. Okay, so we have now the overall reaction is 3 moles of calcium plus 2 moles of chromium ion would give 3 moles of calcium and 2 moles of chromium solid state. Okay, that would be your overall cell reaction, and the cell is spontaneous. Therefore, cell is spontaneous. Okay, next number we are given magnesium as the anode and iron as your cathode. Okay, being the anode, it must undergo oxidation reaction. So we have magnesium. We lose 2 electrons to become magnesium ion. Okay, magnesium undergoing oxidation. The table will give you reduction. So it is positive 2.37 volts because the value for reduction is negative 2.37. Okay, we take the reverse of the sign. The next we have iron. Positive 2 plus 2 electrons will be reduced to iron, the elemental state. Now using your table for electrode potential, we have negative 0.44 volt. We take the sign as is because this is a reduction reaction. So if we take the sum, we have positive 1.93 volts. Okay, since the number of electrons are equal, we don't have to cross multiply them. Okay, we have iron ferrous in the aqueous solution will give you magnesium positive 2 and iron as the electrode, cathode electrode. With a positive value here, therefore, the cell is spontaneous. Okay, next we have here chlorine gas plus 2 bromide ion in an aqueous solution will give you 1 mole of bromine in liquid state and 2 moles of chloride ion. Again, assigning the oxidation number, this is 0 and that is negative 1, 0, combined state, and negative 1. So the one that undergo oxidation is the one that increase its oxidation number. Okay, and that is your bromine. Okay, you have here 2 bromide ion should lose 2 electron, okay, to become 0 state. Negative 2, then you have 0 plus negative 2 is negative 2. So we're balanced. Okay, referring to your reduction potential table for bromine undergoing oxidation, and this is reduction value. So this is negative 1.07 volt. Because the sign is positive, you take the reverse because the reaction is oxidation. So at the cathode, there must be a reduction reaction. Okay, so it is the chlorine gas will accept the 2 electrons given off by the bromide, producing 2 chloride gas ions. Sorry. Okay, so referring to your table for chlorine undergoing reduction, that is positive 1.33 volts. Okay, so capex is. So if you take the sign, this is positive because this is larger. So you have 0 point. You have 2 volts positive. So the overall reaction is you have 2 bromide plus chlorine gas will give you bromine in liquid state and 2 chloride ion in aqueous solution. Now for the electrode for this, we use platinum because this is gases and that is liquid, okay, as the electrode. Both electrodes are made of inert platinum. Then we have a positive potential for the cell having an anode with bromine and the cathode chlorine. Therefore, the cell is spontaneous. We have here a chlorine and bromine. So if we write the electrode reaction or the cell representation. The anode is with your bromine. You have a platinum. You have the bromide. And you have the bromine. You have the salt bridge. Then you have the chlorine gas. You have the platinum and the chloride. Okay. That is how we represent it. We use an inert electrode here. That's all for determining the electrode potential at standard condition. Next time, we will discuss how to get the electrode potential under a non-standard condition.